For thousands of years, humanity has looked toward the heavens with a single question that has never truly been answered. What is reality made of? The ancient Greeks believed everything consisted of four basic elements: earth, air, fire, and water. Later philosophers imagined that matter was built from tiny indivisible particles they called atoms. For centuries, these ideas remained little more than educated guesses, because there was no technology capable of looking deeper into the invisible world. Today, scientists possess machines so powerful they can recreate conditions that existed less than a trillionth of a second after the birth of the universe. Those machines are found beneath the countryside along the border of Switzerland and France, hidden inside a massive underground laboratory known simply as CERN. For some people, CERN represents one of humanity's greatest scientific achievements. For others, it has become the center of some of the strangest mysteries, conspiracy theories, and internet legends ever created. Stories claim CERN has opened portals into other dimensions. Others insist it has altered reality itself. Some believe it has caused the mysterious Mandela effect. Others fear it could create black holes capable of consuming the Earth. Still others claim the laboratory is secretly searching for evidence of parallel universes, or perhaps communicating with them. What is the truth? What is speculation? And why has one scientific laboratory become surrounded by so much mystery? To answer those questions, we must begin not with conspiracy theories, but with history. The story starts in the aftermath of the Second World War. Europe had been devastated. Entire cities lay in ruins. Millions had died. Scientific research had been interrupted for years as many of the continent's brightest minds either fled or were recruited elsewhere. The United States had emerged as a scientific superpower, while European nations struggled to rebuild. Many leading physicists believed Europe needed a place where scientists from every nation could work together peacefully, sharing ideas instead of competing against one another. Their dream was ambitious. Instead of individual countries building expensive laboratories, they would create one enormous international research center. In 1954, that dream became reality. The organization was officially established under its French name, Conseil Européen pour la Recherche Nucléaire. Although the name later changed, the abbreviation remained. CERN. Located near Geneva, Switzerland, the laboratory quickly became one of the world's premier centers for particle physics. Its purpose was surprisingly simple. Understand the smallest building blocks of nature. Everything around us, mountains, oceans, stars, planets, plants, animals, and people, is made from atoms. But atoms themselves are mostly empty space. Inside every atom is a tiny nucleus containing protons and neutrons, surrounded by rapidly moving electrons. For many years, scientists believed these particles were the smallest pieces of matter. Then they discovered they weren't. Protons and neutrons are themselves built from even smaller particles called quarks. Electrons belong to another family of particles entirely. Nature, it seemed, was far more complicated than anyone had imagined. The deeper scientists looked, the stranger reality became. Invisible particles constantly appeared and disappeared. Energy transformed into matter. Matter transformed back into energy. Particles behaved like waves. Waves behaved like particles. The universe no longer resembled the solid, predictable place people once believed it to be. Instead, it looked more like an unimaginably complex ocean of invisible energy. To study these tiny particles required extraordinary tools. Ordinary microscopes could never reveal something smaller than light itself. Scientists needed an entirely different approach. Rather than simply observing particles, they would smash them together at enormous speeds. The idea may sound destructive, but it follows the same principle investigators use when reconstructing a shattered object. Imagine dropping a ceramic vase onto a hard floor. The broken pieces reveal how the vase was constructed. Particle physicists do something similar. By accelerating particles to incredible speeds and allowing them to collide, they study the fragments produced during the impact. Those fragments reveal the hidden structure of nature itself. This approach required machines unlike anything humanity had ever built. Early particle accelerators were relatively small. As technology improved, they became larger and more powerful. Each new machine allowed scientists to probe deeper into the foundations of matter. Eventually, CERN began constructing what would become the largest scientific instrument ever created: the Large Hadron Collider, often shortened simply to the LHC. The scale of the project is difficult to imagine. The accelerator forms a circular tunnel approximately 27 kilometers, or 17 miles, in circumference. It lies about 100 meters beneath the ground. Inside this enormous underground ring, thousands of superconducting magnets guide beams of particles traveling at nearly the speed of light. To function properly, these magnets must be cooled to temperatures colder than outer space. Liquid helium circulates continuously through the system, reducing temperatures to around -271 degrees Celsius. That is only a few degrees above absolute zero, the coldest temperature theoretically possible. At these temperatures, electrical resistance nearly disappears. Immense currents can flow through the magnets without losing energy. The engineering involved is astonishing. More than 9,000 powerful magnets precisely steer the particle beams. Thousands of sensors constantly monitor every component. Vacuum chambers inside the accelerator contain less matter than the emptiness between planets. Every detail must function with extraordinary precision. If the beams drift by even a fraction of a millimeter, years of work could be interrupted. Preparing a collision is remarkably complex. Hydrogen atoms are first stripped of their electrons, leaving only protons. These protons are injected into a series of increasingly powerful accelerators. Each stage boosts their speed. Eventually, they enter the Large Hadron Collider itself. There, two separate beams race around the enormous circular tunnel in opposite directions. Each beam contains billions of protons grouped into tightly packed bunches. They circle the ring more than 11,000 times every second. By the time they reach full speed, they are traveling at approximately 99.999991% of the speed of light. Although nothing with mass can actually reach light speed, these particles come astonishingly close. Powerful magnets keep the beams confined until the precise moment scientists allow them to cross. When the beams intersect inside gigantic detectors, some protons collide head-on. For an unimaginably brief instant, enormous amounts of energy are concentrated into a space far smaller than an atom. According to Einstein's famous equation, E equals mc squared. Energy and matter are interchangeable. Under these extreme conditions, entirely new particles can appear. Many exist for only tiny fractions of a second before decaying into other particles. Sensitive detectors surrounding the collision points record every fragment. The resulting data is staggering. Each second produces information equivalent to thousands of high-definition movies. Sophisticated computer systems immediately discard almost everything, preserving only the most interesting events for analysis. Even then, researchers around the world process petabytes of information every year. No single laboratory could analyze such enormous amounts of data alone. Scientists from more than 100 countries collaborate through an international computing network. It is one of the largest scientific collaborations in history. This global effort has transformed our understanding of the universe. Many particles predicted decades earlier have finally been observed. Others remain frustratingly elusive. Some mysteries appear even deeper than before. One of CERN's greatest achievements has been confirming what physicists call the Standard Model. Despite its modest name, the Standard Model represents one of the most successful scientific theories ever developed. It describes the known fundamental particles and explains how many of the forces governing nature operate. Yet even this remarkable theory has limitations. It does not explain gravity. It cannot account for dark matter. It cannot fully describe dark energy. It leaves unanswered questions about why matter exists at all. In other words, despite decades of extraordinary discoveries, scientists still understand only a small fraction of reality. This realization surprises many people. The public often imagines science has already solved most of the great mysteries of existence. In truth, the opposite is closer to reality. Astronomers estimate that ordinary matter, the atoms making up everything we can see, accounts for only about 5% of the universe. The remaining 95% consists of dark matter and dark energy, two mysterious phenomena that remain largely unexplained. Even after centuries of scientific progress, we still do not know what most of the universe is actually made of. This enormous gap in knowledge naturally invites speculation. Whenever science reaches the edge of the known, imagination begins filling the unknown. Some ideas eventually become accepted discoveries. Others remain fascinating possibilities. Still others drift into mythology and conspiracy theories. Few places illustrate this better than CERN. As the laboratory grew more powerful, stories surrounding it became increasingly extraordinary. Photographs of strange equipment circulated online. Videos were interpreted as evidence of secret rituals. Scientific terminology involving dimensions, antimatter, and quantum mechanics became intertwined with claims of portals, alternate realities, and hidden experiments. Some of these stories originated as jokes. Others were misunderstandings. Still others were deliberate attempts to create sensational internet content. Before long, millions of people around the world believed CERN was involved in activities far beyond particle physics. To understand why these theories became so widespread, we first need to understand the incredible discoveries CERN has actually made. Because, astonishing as the facts already are, they provide the foundation upon which the mysteries and the myths were built. By the late 20th century, physicists had assembled an extraordinary picture of the universe. Decades of experiments had identified an entire family of fundamental particles. Electrons, quarks, neutrinos, photons, gluons, and several other particles all fit together like pieces of a gigantic cosmic puzzle. The Standard Model successfully predicted the behavior of these particles with astonishing precision. Again and again, experiments confirmed its predictions. Yet one enormous question remained unanswered. If these particles truly formed the foundation of reality, why did some possess mass while others did not? Why is an electron relatively light, while a top quark is hundreds of thousands of times heavier? Why does light travel forever at the speed of light, seemingly without mass at all? Without answers to these questions, the Standard Model was incomplete. Back in the 1960s, several physicists working independently proposed a remarkable solution. Among them was a British theoretical physicist named Peter Higgs. The idea was difficult to visualize, but its implications were profound. Imagine walking through an empty room. You move freely because nothing slows you down. Now imagine walking through waist-deep water. Every step requires greater effort. Finally, imagine attempting to walk through thick mud. Movement becomes slow and difficult. Higgs suggested that something similar might exist throughout the entire universe. Instead of empty space being truly empty, perhaps every corner of the cosmos is filled with an invisible field. Particles moving through this field interact with it differently. Some move through it almost effortlessly. Others experience far greater resistance. The stronger the interaction, the greater the particle's mass appears to be. This invisible background became known as the Higgs field. If such a field truly existed, it should occasionally produce a detectable particle. That particle became known as the Higgs Boson. Finding it, however, would prove to be one of the greatest scientific challenges in history. The Higgs boson was expected to exist for only an unimaginably brief instant before decaying into other particles. Detecting it would require collision energies never before achieved. For decades, scientists searched unsuccessfully. Accelerators in Europe, the United States, and elsewhere pushed technology to its limits. Hints appeared. False alarms followed. Each experiment narrowed the possibilities but failed to deliver definitive proof. As the years passed, some physicists began wondering whether the Higgs boson existed at all. Perhaps the theory was wrong. Perhaps nature had chosen a completely different mechanism. Everything depended upon building a machine far more powerful than anything humanity had ever attempted. That machine would become the Large Hadron Collider. Construction began during the 1990s. It required more than a decade of engineering, international cooperation, and billions of dollars in investment. Thousands of scientists, engineers, technicians, electricians, programmers, and construction workers contributed to the project. Every component had to function with astonishing precision. Superconducting magnets weighing dozens of tons were lowered into underground tunnels. Miles of electrical cables connected countless systems. Cryogenic equipment capable of maintaining temperatures colder than deep space was installed throughout the accelerator. Meanwhile, enormous particle detectors were constructed at several collision points. Among them, two became particularly famous: ATLAS and CMS. Although different in design, both detectors pursued the same goal: observe whatever emerged from proton collisions. Calling them detectors hardly conveys their immense size. ATLAS stands nearly as tall as a 7-story building. CMS weighs approximately 14,000 tons. Each contains millions of electronic sensors capable of recording particle interactions occurring in less than a billionth of a second. These instruments are often compared to digital cameras. The comparison is only partially accurate. Instead of photographing visible light, they reconstruct invisible particle events using sophisticated electronics and powerful computer algorithms. Every collision resembles a tiny explosion. Most produce familiar particles already well understood. Scientists were searching for something extraordinarily rare: the signature of the Higgs boson. After years of preparation, the Large Hadron Collider began operating. Expectations were enormous. Then, almost immediately, disaster struck. In September 2008, shortly after initial startup, a faulty electrical connection caused a major accident. Large amounts of liquid helium escaped into the tunnel. Several magnets were severely damaged. The accelerator shut down. Repairs required more than a year. For critics already skeptical of the project, the accident became evidence that the machine was dangerous or cursed. Some newspapers exaggerated the event. Online forums exploded with speculation. Yet the reality was much less mysterious. Complex machines occasionally fail. The incident resulted from engineering problems, not extraordinary physics. After extensive repairs and additional safety improvements, the collider restarted. This time, it performed exactly as designed. Collision energy steadily increased. Data poured into research centers across the globe. Scientists analyzed trillions of particle interactions. Months became years. Tiny statistical hints gradually emerged. Individually, they meant little. Collectively, they suggested something extraordinary might finally be appearing. In particle physics, evidence alone is not enough. Random fluctuations sometimes imitate new discoveries. Researchers therefore require an extremely high statistical standard before announcing success. The accepted threshold is known as 5 sigma. In simple terms, the chance of the result being random must be extraordinarily small. Only then will physicists declare a discovery. Finally, on July 4, 2012, CERN held a highly anticipated seminar. Scientists from around the world watched live broadcasts. Researchers packed lecture halls. Journalists filled every available seat. Peter Higgs himself attended. As data appeared on enormous screens, applause erupted. Both the ATLAS and CMS experiments had independently observed a new particle. Its properties matched those expected for the long-sought Higgs boson. Nearly 50 years after its prediction, the particle had finally been found. Peter Higgs, sitting quietly among the audience, wiped tears from his eyes. One of the greatest scientific predictions in history had been confirmed. The discovery quickly became front-page news worldwide. Headlines referred to the Higgs boson as the God particle. The nickname generated enormous public interest. Ironically, many physicists disliked it. The term had originated from the title of a popular science book and was never intended as a scientific description. The Higgs boson has no connection to religion or divinity. It does not create the universe. It is not evidence of supernatural forces. Nevertheless, the dramatic nickname captured public imagination. Unfortunately, it also fueled countless misunderstandings. Some people concluded scientists had discovered God. Others believed CERN had somehow created life itself. Still others imagined researchers had unlocked ultimate cosmic power. None of these interpretations reflected what had actually occurred. The discovery confirmed the existence of a quantum field that helps explain why certain elementary particles possess mass. It was an extraordinary achievement. But it did not suddenly grant unlimited knowledge or limitless technological abilities. Despite this, conspiracy theories rapidly multiplied. One frequently repeated claim asserted that CERN had recreated the Big Bang. In reality, the comparison is only partly true. The temperatures and energies inside proton collisions briefly resemble conditions that existed fractions of a second after the universe began. However, the amount of energy involved is incredibly small. Each collision contains less energy than many everyday events. The difference lies not in total energy but in how intensely that energy is concentrated into an unimaginably tiny space. This distinction is often misunderstood. Another widespread myth claimed CERN had become capable of creating new universes. This idea emerged because certain theoretical models suggest extremely high energy conditions might resemble those existing during cosmic inflation shortly after the Big Bang. Such discussions occur within advanced theoretical physics. They are mathematical explorations rather than evidence that miniature universes are actually being created beneath Switzerland. Scientific theories frequently examine possibilities. Exploring a possibility does not mean it has been observed. Yet once these ideas reached social media, nuance often disappeared. The phrase "scientists are studying extra dimensions" transformed into "scientists opened a portal." A discussion about quantum vacuum fluctuations became proof reality is unstable. Speculation evolved into certainty. Rumor replaced evidence. The internet accelerated the process. Around the same time, another concern attracted worldwide attention. Could the Large Hadron Collider accidentally create a black hole? The possibility sounded terrifying. If true, could such a black hole swallow the Earth? The question became so widespread that CERN published detailed safety analyses addressing public fears. Ironically, the concern originated from legitimate scientific discussions. Certain speculative theories suggested microscopic black holes might briefly appear during extremely energetic particle collisions. However, if they existed at all, they would be unimaginably tiny and would evaporate almost instantly through a process known as Hawking radiation. More importantly, nature performs far more energetic experiments every day. Cosmic rays, high-energy particles arriving from outer space, constantly strike Earth's atmosphere with energies exceeding those produced by the Large Hadron Collider. These natural collisions have occurred for billions of years. If dangerous microscopic black holes could form under such conditions, Earth, the Moon, the Sun, and every planet would have disappeared long before humans evolved. This simple observation reassures most physicists. Nature has already conducted the experiment countless trillions of times. Nevertheless, dramatic headlines often spread much faster than careful explanations. Fear attracts attention. Mystery attracts viewers. And CERN was becoming increasingly mysterious in the public imagination. Ironically, the laboratory itself encouraged public curiosity. It hosted tours, released educational videos, shared spectacular images of its enormous detectors. Scientists openly discussed unanswered questions. That openness, however, sometimes had an unexpected consequence. When people heard researchers discussing dark matter, extra dimensions, supersymmetry, quantum vacuum energy, or hidden particles, many assumed these concepts were already established facts rather than theoretical possibilities under investigation. The distinction between hypothesis and discovery gradually blurred. Meanwhile, online content creators discovered that almost any story involving CERN attracted enormous audiences. Videos with titles promising secret portals, alien technology, or hidden dimensions accumulated millions of views. Photographs were taken out of context. Scientific terminology was reinterpreted. Coincidences became evidence. Soon, CERN was no longer viewed solely as a research laboratory. For many people, it had become something else entirely. A place where science appeared to touch the boundaries of science fiction. A place where reality itself seemed uncertain. And that uncertainty would soon give rise to one of the most enduring mysteries associated with CERN, the belief that the laboratory was somehow connected to alternate dimensions, parallel universes, and the hidden fabric of reality itself. Part 3. One of the most fascinating aspects of modern physics is that the deeper scientists explore reality, the stranger it becomes. At first glance, the universe appears simple. Solid objects feel solid. Time seems to move steadily forward. Space appears empty. Cause comes before effect. Everything behaves according to familiar rules. Yet almost every one of those assumptions begins to unravel when scientists examine nature at its smallest scales. This is one of the reasons CERN has become surrounded by mystery. Many of the ideas being investigated there sound as though they belong in a science fiction novel. Invisible dimensions. Unknown particles. Quantum fields. Antimatter. Dark matter. Vacuum energy. None of these concepts were invented to entertain the public. They emerged because mathematics and experiments suggest the universe is far more complicated than our everyday experience would indicate. One of the greatest mysteries is something scientists call dark matter. The name itself is misleading. Dark matter is not simply ordinary matter that happens to be dark. It does not absorb light in the normal sense. It does not emit light. It cannot be seen with telescopes. Yet astronomers are convinced that it exists. How can they be so certain? The answer lies in gravity. During the 1930s, astronomers studying large clusters of galaxies noticed something peculiar. The galaxies were moving far too quickly. According to Newton's laws of gravity, they should have flown apart long ago. Instead, they remained bound together. It was as though an enormous amount of invisible mass was holding everything in place. For decades, the observation remained controversial. Then better telescopes became available. Scientists measured the rotation of individual galaxies. Again, something unexpected appeared. Stars near the outer edges of galaxies were moving much faster than expected. According to known physics, those stars should have drifted away into space. Instead, they continued orbiting as if surrounded by a gigantic invisible halo. The simplest explanation was that galaxies contained enormous amounts of unseen matter. Today, nearly every major astronomical observation supports that conclusion. Gravitational lensing. The motion of galaxies. The structure of galaxy clusters. Even subtle patterns left over from the Big Bang. All point toward the existence of invisible matter. Current estimates suggest ordinary atoms make up only about 5% of the universe. Dark matter accounts for roughly 27%. The remaining 68% appears to be something even stranger. Dark energy. Unlike dark matter, dark energy does not seem to hold things together. Instead, it appears to push the universe apart. In 1998, astronomers made an astonishing discovery. They found that the expansion of the universe is accelerating. Galaxies are not merely drifting apart. The expansion itself is speeding up. Something is acting against gravity on the largest scales imaginable. No one knows exactly what that something is. Dark energy is simply the name given to the unknown phenomenon. Together, dark matter and dark energy make up approximately 95% of the universe. Think about that for a moment. Everything we have ever seen. Every planet. Every star. Every cloud. Every mountain. Every human being. Every living creature. Represents only about 5% of reality. The vast majority of the cosmos remains mysterious. This realization alone explains why physicists continue searching for answers. The Standard Model, despite its incredible success, clearly does not tell the entire story. Could CERN discover particles connected to dark matter? Possibly. In fact, many experiments are designed specifically to search for evidence of entirely new particles that fall outside the standard model. No confirmed discovery has yet been made. But the search continues. Another mystery involves antimatter. To understand antimatter, imagine looking into a mirror. Your reflection resembles you in almost every way. Yet left and right appear reversed. Antimatter is not quite a mirror image of ordinary matter, but it behaves in ways that are remarkably symmetrical. Every known particle has an antimatter counterpart. Electrons have positrons. Protons have antiprotons. Neutrons have antineutrons. When matter and antimatter meet, they annihilate each other. Their mass converts almost entirely into energy. Einstein's famous equation predicts exactly this outcome. Scientists have successfully created antimatter for decades. Hospitals routinely use positrons in medical imaging through PET scans. Particle accelerators produce antimatter regularly. Despite this, enormous mysteries remain. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. If that happened, everything should have annihilated. No stars. No planets. No galaxies. No people. Instead, the observable universe consists almost entirely of ordinary matter. Somehow, during the earliest moments after the Big Bang, nature developed a tiny imbalance. For roughly every billion antimatter particles created, there appears to have been 1,000,000,001 matter particles. After mutual annihilation, that tiny excess remained. Everything we see today exists because of that incredibly small difference. Why that imbalance occurred remains one of the greatest unsolved problems in physics. CERN conducts numerous experiments attempting to understand this mystery. Researchers compare matter and antimatter with extraordinary precision. So far, they appear remarkably similar. Yet scientists continue looking for subtle differences that might explain why the universe exists at all. Then there are neutrinos, often called ghost particles. Every second, trillions of neutrinos pass through your body. They come from the sun, from distant stars, from exploding supernovas, from radioactive materials inside Earth itself. And yet you never notice them. That is because neutrinos almost never interact with ordinary matter. A single neutrino could pass through a wall of solid lead stretching for light years without colliding with anything. Detecting them requires gigantic underground laboratories filled with ultra-pure water or other specialized materials. Even then, only a tiny fraction are ever observed. Originally, scientists believed neutrinos possess no mass whatsoever. Then experiments demonstrated something remarkable. Neutrinos can change identities while traveling. This behavior, known as neutrino oscillation, is only possible if they possess at least a tiny amount of mass. That discovery required modifications to the standard model. Nature had once again revealed unexpected complexity. Physicists often joke that every time they believe they understand the universe, it surprises them. One question naturally follows. If the standard model is incomplete, what comes next? Several theories attempt to answer that question. Among the most famous is supersymmetry, usually abbreviated as SUSY. Supersymmetry proposes that every known particle possesses an undiscovered partner. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. These hypothetical particles could help explain dark matter and solve several mathematical problems within particle physics. For years, many physicists expected CERN to discover evidence supporting supersymmetry. So far, no such evidence has appeared. That does not necessarily mean the theory is wrong. Perhaps the particles are simply heavier than expected. Perhaps nature follows an entirely different path. Science often advances by eliminating possibilities. Every unsuccessful search teaches researchers something valuable. Another idea attracting enormous public attention involves extra dimensions. Most people experience three dimensions of space: length, width, height. Time is often considered a fourth dimension within Einstein's theory of relativity. But several advanced theories suggest additional dimensions may exist. String theory, for example, proposes that tiny vibrating strings form the foundation of all particles. To function mathematically, the theory requires additional spatial dimensions beyond those we perceive. Depending upon the version of the theory, the universe may contain 10, 11, or even more dimensions. These dimensions would not resemble hidden rooms waiting to be discovered. Instead, they might be curled into unimaginably tiny scales. Picture a garden hose lying across the ground. From far away, it appears to be a one-dimensional line. An ant walking upon its surface experiences another dimension wrapped around the hose. Similarly, additional dimensions could exist throughout the universe while remaining invisible at human scales. This fascinating possibility often becomes misunderstood. Scientists investigating mathematical models involving extra dimensions are not claiming they have discovered portals. They are exploring theoretical frameworks that might explain observations not accounted for by existing physics. Nevertheless, once terms like hidden dimensions entered popular culture, imagination quickly took over. Books, movies, television shows, internet videos all began presenting extra dimensions as alternate worlds existing beside our own. Some suggested CERN was attempting to reach them. Others claimed the laboratory had already succeeded. In reality, no evidence supports those claims. Researchers are studying mathematics and particle interactions, not opening gateways between universes. Still, the questions remain intriguing. Could other dimensions exist? Possibly. Do we have experimental proof? Not yet. This distinction between possibility and evidence is essential. Science embraces imagination. Many great discoveries begin as bold ideas. But imagination alone is not enough. Ideas must survive experimentation. They must produce measurable predictions. They must withstand independent verification. Without evidence, even the most fascinating hypothesis remains speculation. That careful approach distinguishes science from mythology. Ironically, however, the mysteries explored by CERN are so extraordinary that many people find speculation irresistible. If invisible dimensions might exist, if 95% of the universe remains unknown, if particles appear from pure energy, if quantum mechanics already challenges common sense, then perhaps reality is even stranger than anyone realizes. This line of thinking helped fuel countless internet theories. Some claimed CERN had accidentally punctured reality. Others insisted researchers had briefly opened microscopic portals. Still others believed strange changes around the world were evidence that the laboratory's experiments were affecting the fabric of existence itself. Among all of these ideas, one theory would become especially famous. It suggested that CERN had somehow altered history itself. That people remembered events from entirely different realities. That millions of individuals had unknowingly crossed into alternate timelines. It became known as the Mandela effect. And for many believers, CERN stood at the center of the mystery. Part 4. Imagine waking one morning and discovering that something you have remembered your entire life has somehow changed. A favorite childhood book contains different words. A famous movie quote is no longer the way you remember it. The logo of a well-known company looks subtly different. A historical event seems to have occurred on another date. At first, you assume you simply misremembered. Then you discover thousands, sometimes millions, of other people remember exactly the same thing. This strange phenomenon has become known as the Mandela effect. For many people, it represents nothing more than an interesting example of how human memory works. For others, it is evidence that reality itself has somehow changed. And somewhere along the way, CERN became one of the central characters in that story. The origin of the Mandela effect can be traced back to 2009. Paranormal researcher Fiona Broom attended a conference where she spoke with several people who vividly remembered former South African President Nelson Mandela dying in prison during the 1980s. The memory seemed remarkably detailed. Many recalled television news reports, funeral coverage, public mourning. Some even remembered speeches that had supposedly been broadcast around the world. There was only one problem. None of it had happened. Nelson Mandela had been released from prison in 1990. He later became South Africa's first democratically elected president. He remained active in public life for decades and died in 2013. How could so many people confidently remember an event that never occurred? Broom coined the phrase Mandela effect to describe shared false memories. At first, the topic remained relatively obscure. Then social media transformed it into a global phenomenon. Soon, thousands of examples appeared online. One of the most famous involves the children's book series The Berenstain Bears. Many adults insist they clearly remember the books being titled The Berenstain Bears. The spelling feels familiar. It seems correct. Yet every original publication reads Berenstain. Another well-known example concerns the Monopoly mascot. Many people remember him wearing a monocle. They picture the wealthy character complete with top hat, mustache, tuxedo, and a monocle. Except he never wore one. The image exists only in memory. Movie quotes provide countless additional examples. Many people confidently remember Darth Vader saying, "Luke, I am your father." In reality, the line is, "No, I am your father." The altered version became so widespread through comedians, television shows, and everyday conversation that it eventually replaced the original in popular memory. Another classic example comes from the film Casablanca. Millions remember the line, "Play it again, Sam." Yet that exact sentence never appears in the movie. The actual dialogue is quite different. Then there is Snow White. How many people remember the evil queen asking, "Mirror, mirror on the wall"? In the original Disney film, the line begins, "Magic mirror on the wall." These examples continue almost endlessly. Brand logos, song lyrics, historical events, geography, famous paintings, company names, even the position of continents on maps. Entire online communities have formed around comparing memories that differ from documented reality. Most psychologists offer a straightforward explanation. Human memory is not like a video recording. Every time we remember something, the brain reconstructs it. During that reconstruction, details can gradually change. Over time, inaccurate information may become incorporated into genuine memories. This process is known as reconstructive memory. Decades of research demonstrate how easily memory can be influenced. Participants in laboratory experiments have developed vivid memories of events that never occurred. Some become convinced they were once lost in shopping malls as children. Others remember meeting fictional characters. Still others recall entirely fabricated news events. These false memories often feel just as real as authentic ones. Confidence alone does not guarantee accuracy. Our brains naturally fill in missing details. They simplify information. They combine similar experiences. They unconsciously alter memories each time they are recalled. From a psychological perspective, the Mandela effect represents a fascinating demonstration of these processes. Yet not everyone accepts that explanation. Alternative theories began appearing online. Some suggested parallel universes. Others proposed simulated reality. Some believed time travel had altered history. Eventually, another possibility entered the discussion. Perhaps CERN was responsible. The timing seemed suspicious to many observers. The Large Hadron Collider began operating in 2008. The term Mandela effect appeared shortly afterward. Internet discussions about altered memories expanded rapidly during the following years. Could there be a connection? Supporters pointed to CERN's research into quantum mechanics, particle collisions, high-energy physics, references to extra dimensions. To them, it seemed plausible that experiments involving enormous energies might somehow affect reality itself. Some claimed the collider had briefly shifted humanity into a neighboring timeline. Others suggested repeated experiments were producing tiny changes that accumulated over time. According to these theories, history itself had been subtly rewritten. People retained fragments of memories from previous versions of reality. It is certainly an imaginative hypothesis. But does any evidence support it? Not according to current science. Particle collisions inside the Large Hadron Collider occur on unimaginably tiny scales. Their effects are measured within microscopic detectors. Nothing observed during these experiments suggests that memories, history, or macroscopic reality have been altered. Furthermore, many examples of shared false memories existed long before CERN began operating. Human beings have always remembered events incorrectly. What changed was the internet. Before social media, people rarely compared detailed memories with millions of strangers. If someone misremembered a movie quote decades ago, the mistake often went unnoticed. Today, one person posts an incorrect memory online. Thousands recognize it. Millions discuss it. The illusion becomes far more visible. The internet allows shared misconceptions to spread with unprecedented speed. Psychologists also point to another important factor. Many Mandela effect examples involve information that seems more logical than reality. Take the Monopoly mascot. People associate monocles with wealthy gentlemen from old cartoons. The character already wears a tuxedo and top hat. Adding a monocle feels natural. The brain unconsciously completes the image. Similarly, Luke, I am your father immediately identifies the speaker and listener. Outside the context of the film, it makes more sense than the original dialogue. The altered version is easier to repeat. Eventually, it replaces the authentic quote in popular culture. The same pattern appears repeatedly. Our brains often prefer information that seems more complete or more familiar. That tendency can create surprisingly convincing false memories. Still, some Mandela effect cases remain genuinely puzzling. Researchers continue studying why certain incorrect memories become so widespread. The phenomenon reveals just how complex and imperfect human memory truly is. For conspiracy theorists, however, these explanations seem insufficient. They argue that millions of identical false memories are too extraordinary to dismiss. Some point toward quantum mechanics. Others invoke parallel universes. Many return once again to CERN. One frequently cited argument involves quantum theory itself. Quantum particles behave probabilistically. Until measured, their behavior can only be described mathematically. Some popular interpretations suggest multiple outcomes may coexist. This idea became linked to the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event produces branching realities. In one universe, a radioactive atom decays. In another, it does not. Applied to everyday life, the concept becomes astonishing. Every decision, every possibility, every quantum event could produce another branch of reality. Science fiction eagerly embraced the concept. Movies, television series, novels, and comic books explored worlds where alternate histories coexist. Eventually, internet discussions merged the many worlds interpretation with CERN. If countless universes already exist, and CERN studies quantum phenomena, could the laboratory somehow cause branches to intersect? Could neighboring realities overlap? Could memories occasionally cross between timelines? These questions capture the imagination, but they remain entirely speculative. The many worlds interpretation is one philosophical interpretation of quantum mechanics. It is not experimentally confirmed. Even if it were correct, it does not predict people remembering alternate histories or laboratories shifting between universes. The mathematics simply does not support those conclusions. Nevertheless, speculation continued growing. Videos accumulated millions of views. Articles connected unrelated events. Coincidences became patterns. Patterns became certainty. Soon the Mandela effect was no longer merely about memory. It had become part of a much larger narrative. A narrative involving hidden dimensions, parallel realities, quantum experiments, secret government research, and a mysterious laboratory beneath the Swiss countryside. Whether or not any of these extraordinary claims were true, one fact was undeniable. CERN had become far more than a scientific institution in the public imagination. It had become a symbol. A place where the known world seemed to end, and where the unknown might begin. Yet another series of events would deepen that mystery even further. Not because of particle collisions, but because of a handful of strange videos, unusual artwork, and images that spread across the internet, convincing many people that something secretive was taking place behind CERN's gates. Part 5. Long before social media, scientific laboratories rarely attracted public attention. Most research facilities were quiet places where scientists spent years conducting experiments that few people outside their field ever noticed. CERN was different. It was enormous. It welcomed visitors. It produced spectacular photographs. It regularly published videos explaining its work. Thousands of researchers from around the world passed through its gates every year. Ironically, that openness would help create some of the most enduring mysteries surrounding the laboratory. One of the first images that attracted widespread attention was not a scientific instrument at all. It was a statue. Standing outside one of CERN's buildings is a bronze statue depicting the Hindu deity Shiva. For many visitors, it was simply an impressive work of art. For others, it became the centerpiece of countless conspiracy theories. To understand why, it helps to know who Shiva is within Hindu tradition. In Hinduism, Shiva is one of the principal deities. He is often associated with transformation, renewal, meditation, and the continual cycle of creation and destruction that governs the universe. One of his best-known forms is known as Nataraja, the Lord of the Dance. In this depiction, Shiva dances within a ring of flames. The dance symbolizes the eternal rhythm of the cosmos. Creation, preservation, destruction, and rebirth. To physicists, the symbolism was surprisingly appropriate. Modern particle physics reveals a universe in constant motion. Particles appear. Particles disappear. Energy transforms into matter. Matter transforms back into energy. Everything exists within an endless cycle of change. Because of these parallels, the government of India presented the Shiva statue to CERN in 2004 as a symbol of international cooperation and the shared human pursuit of understanding the universe. A plaque beside the sculpture explains this connection. For scientists working at CERN, the statue represented philosophy, culture, and the beauty of scientific exploration. For conspiracy theorists, however, the symbolism appeared much darker. Videos soon appeared online claiming CERN had deliberately placed a god of destruction outside the laboratory because researchers intended to destroy the world. The argument sounded convincing to those unfamiliar with Hindu beliefs. Yet it overlooked one important fact. Within Hindu philosophy, destruction is not viewed as purely negative. It represents transformation. Old forms must sometimes disappear so new ones may emerge. The symbolism differs greatly from the purely destructive meaning often assumed in Western interpretations. Nevertheless, the statue became one of the most frequently cited pieces of evidence in online conspiracy videos. Then came another incident. This one was stranger. In 2016, security cameras at CERN recorded several people entering the grounds late at night. The video appeared to show individuals dressed in dark clothing performing what looked like a ritual near the Shiva statue. One participant appeared to stab another while witnesses stood nearby. The footage spread across the internet almost immediately. Millions watched. Many concluded they had witnessed an authentic occult ceremony taking place inside one of the world's most important scientific laboratories. News organizations began asking questions. CERN investigated. The explanation turned out to be considerably less mysterious. The individuals involved were believed to be employees or visiting researchers who had staged the event as a prank. No one had actually been harmed. The apparent victim was acting. The fake knife and theatrical performance were intended as a joke. Those responsible violated CERN's rules by entering restricted areas after hours. The organization condemned the incident. Still, the damage had already been done. Once released online, the video took on a life of its own. For believers, CERN's explanation became part of the cover-up. The fact that it had been called a prank simply confirmed, in their minds, that something secretive had occurred. This pattern appears frequently in conspiracy theories. Any official explanation becomes interpreted as further evidence of deception. As a result, the theory becomes almost impossible to disprove. Another event that fueled speculation was far more lighthearted. In 2016, CERN employees created a humorous video celebrating the return of the Large Hadron Collider after maintenance. The short film featured scientists dancing through hallways while holding signs. One sign read, "Bond number 1." Another simply displayed the word, "Mandela." The video ended with laughter. It was clearly intended as playful office humor. Yet online investigators quickly examined every frame. Why did one scientist hold a sign reading Mandela? Was this proof that CERN secretly acknowledged the Mandela effect? Others focused on a sequence involving a mock newspaper. Still others analyzed background objects, hand gestures, and facial expressions. Entire documentaries were produced claiming the video contained hidden messages. When viewed objectively, however, the film resembles what many workplaces create for employee celebrations. Inside jokes, scientific humor, playful references. Without prior assumptions, the scenes appear entirely ordinary. But once viewers expected to find hidden meanings, every detail became significant. Psychologists call this apophenia. The tendency to perceive meaningful patterns where none actually exist. It is the same psychological process that allows people to see faces in clouds, animals in rock formations, or hidden codes in random numbers. The human brain evolved to recognize patterns. Most of the time, this ability is extremely useful. Occasionally, it leads us to connect unrelated events. CERN's openness created countless opportunities for this phenomenon. Researchers posted photographs. Visitors shared videos. Scientific presentations introduced unfamiliar terminology. Each new image became potential material for speculation. One phrase repeatedly misunderstood involved opening new windows into the universe. Scientists often use expressions like this metaphorically. A more powerful telescope opens a new window into space. A microscope opens a new window into biology. Likewise, a particle accelerator opens a new window into fundamental physics. Conspiracy theorists sometimes interpreted these statements literally. If scientists were opening windows, perhaps they were opening portals. The distinction disappeared. Another source of confusion involved the word vacuum. Inside the Large Hadron Collider, particles travel through ultra-high vacuum tubes. To physicists, a vacuum simply means an environment containing extremely little matter. To the public, the term sometimes suggested empty space capable of extraordinary phenomena. Quantum physics complicated matters further. Physicists often explain that the quantum vacuum is not truly empty. Instead, it contains fluctuating quantum fields. Virtual particles briefly appear and disappear. This language sounds astonishing. It also sounds mysterious. Yet within quantum field theory, these concepts have precise mathematical meanings. Unfortunately, scientific terminology rarely survives intact once translated into headlines or social media posts. The same problem occurred with another phrase frequently associated with CERN: the fabric of space-time. Einstein demonstrated that space and time are connected. Massive objects curve this four-dimensional geometry. Gravity emerges from that curvature. Scientists sometimes describe this as the fabric of space-time. Again, the wording is metaphorical. There is no literal cloth covering the universe. Yet popular culture often visualizes space-time as an actual fabric that could be torn, punctured, or ripped open. From there, the leap to portals becomes much smaller. One misunderstood scientific concept after another gradually accumulated. Each misunderstanding reinforced the next. By themselves, none proved anything extraordinary. Together, they created a compelling narrative. A laboratory studying hidden dimensions. A statue representing cosmic transformation. A mysterious nighttime ritual. Playful videos containing unusual symbols. Scientists discussing quantum fields. Talk of invisible particles. References to the earliest moments after the Big Bang. To many observers unfamiliar with particle physics, the pieces appeared to fit together. Whether they actually did became almost secondary. The story itself was captivating. Meanwhile, genuine scientific discoveries continued quietly in the background. Researchers improved measurements of known particles. They searched for evidence of dark matter. They investigated antimatter with increasing precision. Most headlines about these achievements attracted modest attention. By contrast, a single rumor involving portals or alternate realities could spread across the globe within hours. This imbalance reflects something fundamental about human nature. Mysteries are exciting. Secrets are irresistible. Simple explanations often feel unsatisfying compared to extraordinary possibilities. Yet genuine science is often more remarkable than fiction. The fact that invisible particles pass through our bodies every second. That space itself can curve. That time slows at high speeds. That energy becomes matter. These are not fantasies. They are experimentally verified realities. The challenge lies in distinguishing where established science ends and speculation begins. As CERN continued exploring the smallest building blocks of existence, another subject repeatedly entered public discussion. Could the laws of physics themselves allow travel through time? Could wormholes exist? Might parallel universes be more than mathematics? And if such extraordinary phenomena were possible, could humanity ever hope to reach them? These questions would push the conversation far beyond conspiracy theories, into some of the deepest mysteries modern physics has ever contemplated. Part 6. Ever since Albert Einstein published his theory of relativity in the early 20th century, our understanding of time has never been the same. Before Einstein, time was generally thought of as universal. A clock in London. A clock in New York. A clock aboard a moving train. All were assumed to measure the same flow of time. Einstein demonstrated that reality is far stranger. Time is not fixed. It is flexible. It stretches. It slows. It speeds up depending upon motion and gravity. This idea sounds almost unbelievable, yet it has been confirmed countless times. Modern GPS satellites must account for relativistic effects every day. Without those corrections, navigation systems would drift by several miles within 24 hours. Relativity is not merely a theory. It is part of the technology millions of people rely upon every day. One of the most fascinating consequences of relativity is time dilation. Imagine two identical twins. One remains on Earth. The other travels through space at an enormous fraction of the speed of light. When the traveler returns, less time has passed for the astronaut than for the sibling who stayed behind. To the traveler, the journey may have lasted only a few years. Back on Earth, decades may have passed. This is not science fiction. It follows directly from Einstein's equations and has been verified using highly accurate atomic clocks. Particles inside accelerators experience this effect continuously. Muons, unstable particles normally surviving only tiny fractions of a second, live significantly longer when traveling near the speed of light. Scientists measure this effect routinely. The Large Hadron Collider therefore demonstrates that time behaves differently under extreme conditions. However, this often leads to an important misunderstanding. Time dilation does not mean CERN enables travel into the past. The particles experience time differently because of their tremendous speed. Nothing suggests the experiments send objects backward through history. Nevertheless, once people hear that time slows down inside a particle accelerator, imagination naturally begins asking larger questions. If time can slow, could it stop? Could it reverse? Could someone eventually travel backward? Physicists have explored these questions for decades. Interestingly, the mathematics of general relativity allows some astonishing possibilities. One of the most famous involves wormholes. Imagine folding a sheet of paper. Two distant points suddenly touch. Instead of traveling across the entire surface, you simply pass through the fold. A wormhole represents something similar within spacetime. Rather than moving through ordinary space, it would create a shortcut connecting distant regions of the universe. The concept first appeared within legitimate mathematical solutions to Einstein's equations. Later, physicists Albert Einstein and Nathan Rosen described a theoretical structure now known as the Einstein-Rosen bridge. Science fiction quickly embraced the idea. Movies portrayed spacecraft leaping across galaxies through glowing tunnels. Television series featured travelers visiting other universes. Books imagined civilizations using wormholes as cosmic highways. Yet the scientific reality remains uncertain. Although Einstein's equations permit mathematical solutions resembling wormholes, no naturally occurring traversable wormhole has ever been observed. Even more challenging, keeping such a passage open appears to require something extraordinary. Negative energy. Or what physicists often call exotic matter. Unlike ordinary matter, exotic matter would possess unusual properties not yet observed in forms capable of stabilizing a wormhole. Quantum physics predicts certain situations where negative energy densities may briefly occur. The famous Casimir effect provides one example. Two closely spaced metal plates can alter quantum fluctuations in measurable ways. However, the tiny amounts involved bear no resemblance to what would likely be required to hold open a wormhole large enough for anything to pass through. At present, wormholes remain theoretical possibilities rather than engineering projects. This distinction is crucial. Mathematics sometimes permits structures that nature never actually produces. Black holes offer another example of how theory eventually became reality. For decades, they existed only as mathematical predictions. Today, astronomers routinely observe their effects. Even the shadow of a black hole has now been photographed. Could wormholes someday follow a similar path? Possibly. But no evidence currently demonstrates their existence. Despite this uncertainty, CERN is frequently accused of attempting to create wormholes. Where did this idea originate? Part of the answer lies in scientific terminology. Researchers occasionally discuss extremely energetic collisions producing conditions similar to those existing shortly after the Big Bang. Others investigate theories involving microscopic extra dimensions. These legitimate scientific discussions became transformed online into claims that CERN was deliberately opening gateways between worlds. In reality, no experiment conducted at CERN has produced evidence of a traversable wormhole. Nor has any experiment suggested portals connecting parallel universes. Still, advanced theoretical physics contains ideas that sound remarkably exotic. One such idea is the holographic principle. According to this proposal, our familiar three-dimensional universe might, in some sense, emerge from information encoded upon a distant two-dimensional boundary. The concept arose from studies of black holes and quantum gravity. It remains one of the most fascinating ideas in modern theoretical physics. Although difficult to visualize, it illustrates an important point. The universe may operate according to principles very different from ordinary intuition. Another intriguing concept is quantum entanglement. Albert Einstein famously referred to it as spooky action at a distance. When two particles become entangled, measuring one immediately determines the corresponding property of the other, regardless of the distance separating them. Experiments have confirmed entanglement repeatedly. Yet it does not permit faster-than-light communication. Nor does it transmit usable information instantaneously. Instead, it reveals that quantum reality possesses relationships unlike anything found in everyday experience. Once again, the genuine science is extraordinary enough without additional embellishment. Nevertheless, speculative theories often build upon these authentic discoveries. Some claim entanglement proves consciousness can travel outside the body. Others suggest it enables communication across dimensions. Still others argue CERN uses quantum entanglement to interact with alternate realities. None of these conclusions follows from the experimental evidence. Quantum mechanics remains mysterious. But mysterious does not mean magical. The mathematics is rigorous. The experiments are repeatable. The interpretations remain debated. Another topic frequently associated with CERN involves miniature black holes. As discussed earlier, some speculative models suggested extremely energetic particle collisions might briefly produce microscopic black holes. The media quickly transformed this into alarming headlines. Could Earth be swallowed? Could gravity spiral out of control? Scientists responded by pointing out something both simple and reassuring. Nature has already performed this experiment countless times. High-energy cosmic rays constantly strike Earth's atmosphere with energies sometimes exceeding those produced inside the Large Hadron Collider. These natural collisions have occurred for billions of years. The Moon has experienced them. Mars has experienced them. The Sun experiences them. Every planet in the observable universe likely experiences similar collisions. If dangerous black holes resulted, the cosmos would look very different today. Instead, nothing of the sort has been observed. Even if microscopic black holes could briefly form, current theories indicate they would evaporate almost instantly through Hawking radiation. Stephen Hawking proposed that black holes are not entirely black. Quantum effects near the event horizon cause them to lose energy over time. Small black holes evaporate extraordinarily quickly. Large astrophysical black holes require timescales vastly longer than the current age of the universe. Tiny hypothetical black holes would disappear almost immediately. Again, this illustrates an important feature of scientific reasoning. Physicists do not merely ask whether something is theoretically possible. They calculate consequences. They compare predictions with observations. They evaluate whether nature behaves accordingly. When predictions fail, theories must be revised. Speculation alone is never enough. Despite these careful methods, one question continued captivating the public. Could CERN accidentally discover evidence of another universe? Modern cosmology offers several possibilities. Inflationary cosmology suggests our universe underwent astonishingly rapid expansion shortly after the Big Bang. Some versions of this theory imply that inflation may continue elsewhere, producing countless bubble universes. String theory allows additional possibilities involving higher dimensional spaces. The many-worlds interpretation of quantum mechanics envisions branching realities. Each idea emerges from legitimate attempts to solve difficult mathematical problems. Yet none has been experimentally confirmed. This distinction is often lost in popular discussions. A theoretical possibility becomes described as a hidden fact. An equation becomes interpreted as evidence. Soon, speculation begins sounding indistinguishable from established science. CERN itself remains remarkably cautious. Researchers routinely emphasize uncertainty. Scientific papers discuss confidence levels, alternative explanations, statistical significance, potential sources of error. Such caution rarely generates viral headlines. Bold claims spread much faster. As a result, CERN increasingly found itself portrayed as a place where impossible things were secretly happening. A machine capable of bending time, opening portals, touching parallel universes, changing reality. Yet behind the dramatic stories, thousands of scientists continued pursuing a much quieter goal: understanding nature one experiment at a time. Still, even the most careful science cannot entirely prevent imagination from filling the gaps where knowledge ends. And nowhere were those gaps more intriguing than in the unanswered questions surrounding consciousness itself. Could the human mind perceive realities beyond ordinary space and time? Could quantum physics somehow explain consciousness? Or were these entirely separate mysteries that had simply become intertwined in the public imagination? Those questions would lead us into one of the most controversial intersections between modern physics, philosophy, and speculation. Part 7. If there is one mystery that has fascinated humanity as much as the origin of the universe, it is the mystery of consciousness. What is awareness? Why do we experience thoughts, emotions, memories, and imagination? How does a collection of atoms inside the human brain produce the rich inner world that each of us experiences every moment of our lives? Despite centuries of philosophy and decades of neuroscience, no complete answer exists. Scientists understand a great deal about how neurons communicate. They can observe electrical activity throughout the brain. They can identify regions responsible for vision, language, hearing, memory, and movement. Yet one profound mystery remains. Why should electrical signals inside the brain create subjective experience at all? This question is sometimes called the hard problem of consciousness. It is one of the deepest unsolved questions in science. Because consciousness remains mysterious, it has frequently become linked to quantum mechanics. The connection is understandable. Quantum physics is strange. Consciousness is mysterious. Many people assume the two must somehow be related. Over the years, numerous theories have proposed exactly that. Some scientists have explored whether quantum effects might play a role in brain function. Others have argued that consciousness emerges entirely from classical biological processes, with no special quantum explanation required. The debate continues. What is important to understand is that no widely accepted scientific theory currently demonstrates that consciousness depends upon quantum mechanics. Nor has CERN ever conducted experiments attempting to prove such a connection. Nevertheless, quantum consciousness became a popular subject in books, documentaries, and internet discussions. Some theories went even further. They suggested consciousness might exist independently of the brain. Others proposed that human awareness could somehow influence reality itself. Some argued that observation causes the universe to choose its state. These ideas often trace back to one of the most misunderstood concepts in quantum mechanics: the observer effect. When people first hear the phrase, they frequently imagine that human consciousness somehow creates reality. The actual scientific meaning is rather different. In quantum mechanics, observing a particle requires an interaction. For example, shining light on an electron changes its behavior because photons interact with it. The measuring device, not necessarily a conscious observer, becomes part of the experiment. The mathematics describes how measurement influences quantum systems. It does not require a human mind to magically create existence. Yet this subtle distinction has often disappeared in popular culture. Soon, headlines began claiming, "Consciousness creates reality." Books suggested that thoughts directly shape the physical universe. Some extended these ideas even further. If consciousness influences reality, and CERN studies quantum mechanics, perhaps CERN is somehow manipulating consciousness itself. No scientific evidence supports such claims. Still, they spread rapidly because they combine two of humanity's greatest mysteries into a single narrative: the mystery of the universe and the mystery of the mind. Around the same time, another remarkable hypothesis gained popularity: the simulation hypothesis. The basic idea is surprisingly simple. What if our universe is not fundamental reality? What if everything we experience is part of an unimaginably advanced computer simulation? The concept has ancient philosophical roots. Thousands of years ago, philosophers questioned whether our senses accurately reflected reality. In the 17th century, René Descartes wondered whether an evil deceiver might be creating an illusion. In modern times, philosopher Higgs Boson proposed a more technological version. If future civilizations become advanced enough to simulate entire universes, and if they create enormous numbers of such simulations, then statistically, simulated realities might greatly outnumber original ones. If that were true, perhaps we ourselves are more likely to exist inside a simulation than outside one. The argument is philosophical rather than experimental. No evidence currently confirms that we inhabit a simulation. Yet the idea captured the imagination of millions. Movies such as The Matrix introduced similar concepts to popular audiences. Video games demonstrated increasingly realistic virtual worlds. Artificial intelligence advanced rapidly. The boundary between reality and simulation seemed less obvious than ever before. Eventually, CERN entered the conversation once again. Some theorists speculated that high-energy particle collisions might reveal tiny imperfections in the underlying program. Others imagined that strange experimental results represented glitches in the simulation itself. These ideas make for fascinating fiction. However, no experimental evidence from CERN has revealed computational artifacts, hidden programming code, or signs that reality is simulated. Scientists continue analyzing enormous quantities of data. Thus far, nature behaves according to the known laws of physics. Those laws may eventually require revision. But no evidence currently suggests a computer-generated universe. Then there is another enduring mystery. Déjà vu. Nearly everyone has experienced it. You enter a room. Meet a stranger. Hear a conversation. Suddenly you feel absolutely certain that you have lived through the exact moment before. The sensation may last only seconds. Yet it often feels remarkably convincing. Psychologists generally explain déjà vu as a temporary mismatch between memory systems. The brain mistakenly interprets a new experience as familiar. Neurological studies support this explanation. Nevertheless, some people interpret déjà vu differently. Perhaps it represents a glimpse into another timeline, a memory from a parallel universe, or evidence that reality has shifted. Again, CERN occasionally appears within these discussions. Some internet theories suggest that powerful particle collisions subtly alter the timeline. According to these claims, déjà vu represents brief awareness of those changes. No scientific evidence supports this interpretation. Yet the idea persists because it offers an intriguing explanation for a common human experience. Our minds naturally seek patterns. When something feels mysterious, we search for causes. Sometimes those causes are correct. Sometimes they are imaginative. Another subject frequently connected with CERN involves reports of so-called reality glitches. People describe objects disappearing and reappearing. Unexpected coincidences. Apparent changes in geography. Differences in historical photographs. Altered logos. Changed memories. Many of these reports resemble Mandela effect discussions. Others involve entirely personal experiences. Psychologists point out that human perception is remarkably selective. We notice unusual events far more readily than ordinary ones. Memory continually reconstructs experience. Expectation shapes perception. Attention determines what we remember. These well-documented cognitive processes explain many reported anomalies. That does not necessarily eliminate every mystery. Human perception remains extraordinarily complex. But complexity should not be confused with evidence for altered timelines. One fascinating lesson emerges repeatedly throughout these discussions. Reality is often stranger than intuition. Quantum mechanics genuinely challenges common sense. Relativity genuinely alters time. Space genuinely curves. Black holes genuinely exist. Invisible particles genuinely pass through our bodies by the trillions every second. Because genuine science already sounds extraordinary, fictional additions often seem almost plausible. This creates fertile ground for speculation. CERN itself has repeatedly emphasized its actual mission: to understand the fundamental laws governing nature, to investigate particles, forces, energy, the earliest moments of cosmic history. Researchers there are not searching for supernatural phenomena. They are not attempting to contact alternate realities. They are not conducting experiments on human consciousness. Their published work focuses upon measurable, repeatable physical phenomena. Even so, the laboratory continues inspiring countless theories. Some of those theories are harmless entertainment. Others encourage healthy curiosity about science. A few drift into misinformation. Distinguishing among them requires careful thinking. Extraordinary claims demand extraordinary evidence. At present, no verified experiment demonstrates that CERN has altered human consciousness, shifted timelines, or affected reality beyond the microscopic particle interactions it was designed to study. Yet one category of mystery remains. Unlike consciousness or simulations, this one lies squarely within mainstream physics. It concerns questions scientists openly admit they cannot yet answer. What happened before the Big Bang? Why do the laws of physics have the values they do? Could there be other universes beyond our observable horizon? What is dark matter? What is dark energy? These are not internet myths. They are genuine scientific mysteries. And solving them may require discoveries every bit as revolutionary as those that transformed physics during the 20th century. The next chapter explores those unanswered questions and why many physicists believe the greatest discoveries in the history of science may still lie ahead. Part 8. Throughout the history of science, every major breakthrough has transformed the way humanity understands its place in the universe. When Nicholas Copernicus proposed that Earth revolves around the Sun, our world was no longer the center of creation. When Isaac Newton described gravity, the motion of the heavens became understandable through mathematics rather than mystery. When Charles Darwin explained evolution, humanity's relationship with the natural world changed forever. Then came Einstein. Space and time, once thought to be fixed and absolute, became flexible. The universe itself became dynamic. Each revolutionary idea answered old questions while creating entirely new ones. Today, physicists believe another revolution may be approaching. The Standard Model explains an enormous amount about nature. Yet everyone agrees it is incomplete. Imagine reading a novel with the final third missing. The story makes sense. The characters are believable. Many mysteries are solved. But the ending is absent. That is roughly how many physicists view modern particle physics. It works astonishingly well. But it clearly leaves something out. One of the greatest missing pieces is gravity. Gravity is familiar. We experience it every second of our lives. It keeps our feet on the ground. It guides the moon around Earth. It governs the motion of galaxies. Yet gravity refuses to fit neatly into quantum mechanics. The Standard Model successfully describes three of nature's four known fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force. Gravity remains the exception. Einstein described gravity as the curvature of spacetime. Quantum mechanics describes the other forces through the exchange of particles. Combining these two magnificent theories into one consistent framework has challenged physicists for nearly a century. Some researchers believe the answer lies within string theory. Others investigate loop quantum gravity. Still others explore entirely different mathematical approaches. No single theory has yet emerged victorious. This search is one reason CERN continues operating. Every new experiment helps narrow the possibilities. Sometimes discoveries occur exactly where expected. Sometimes nature surprises everyone. History suggests the biggest breakthroughs often arrive unexpectedly. The discovery of radioactivity, the expansion of the universe, cosmic microwave background radiation, quasars, pulsars. None were anticipated in the form they were eventually found. Physicists therefore remain cautious. The next great discovery could appear anywhere. Perhaps hidden inside an unusual particle decay. Perhaps within subtle asymmetries involving antimatter. Perhaps in data already collected but not yet fully understood. This uncertainty is both frustrating and exciting. Then there is dark matter. For decades, astronomers have accumulated overwhelming evidence that something invisible surrounds galaxies. Yet despite years of searching, no one has directly detected the particle or particles responsible. Numerous possibilities exist. Weakly interacting massive particles, often abbreviated as WIMPs. Axions. Sterile neutrinos. Entirely new categories of matter not yet imagined. CERN searches for clues by recreating conditions where such particles might briefly appear. One possibility is surprisingly clever. Suppose a collision produces a particle that barely interacts with ordinary matter. The detectors might never see it directly. Instead, scientists would notice something missing. Momentum and energy would fail to balance as expected. The invisible particle would reveal itself through what it carried away. This approach resembles investigating an invisible thief. You never see the person. You notice only that valuable objects have disappeared. From the missing evidence, investigators infer what must have happened. Particle physicists often work in exactly this way. Some of the universe's most important discoveries have been made by observing what is absent rather than what is visible. Another fascinating frontier involves neutrinos. These elusive particles continue surprising scientists. They pass effortlessly through planets. They barely interact with matter. Yet they possess mass. Why? No complete explanation currently exists. Some physicists suspect neutrinos may provide clues to physics beyond the standard model. Others believe they could help explain why matter dominates over antimatter. Experiments around the world continue investigating these mysterious particles. CERN contributes to several of these efforts through powerful neutrino beams sent toward distant underground detectors. These experiments may eventually answer questions that have puzzled scientists for generations. While researchers pursue these genuine scientific mysteries, public fascination with conspiracies has hardly diminished. Every major shutdown of the Large Hadron Collider generates new speculation. Whenever upgrades are announced, social media fills with predictions. Some claim reality will change again. Others warn of dimensional portals. Still others predict catastrophic accidents. Then the collider resumes operation. Scientists collect data. The world continues much as before. Yet the theories rarely disappear. This illustrates an interesting feature of conspiracy thinking. When predictions fail, the underlying belief often survives. New explanations emerge. Perhaps the experiment was secretly different. Perhaps the effects were hidden. Perhaps governments concealed the evidence. Such reasoning makes theories difficult to falsify. Scientific thinking follows a different path. Predictions must succeed repeatedly. Experiments must be reproducible. Independent researchers must obtain similar results. If predictions consistently fail, theories are revised or abandoned. This willingness to change ideas based upon evidence lies at the heart of science. It is not a weakness. It is one of science's greatest strengths. History provides many examples. Scientists once believed the universe was static. Evidence showed otherwise. Physicists once assumed neutrinos had no mass. Experiments proved they do. Astronomers once believed galaxies were the only large structures in the cosmos. Later observations revealed enormous galaxy clusters, superclusters, and a vast cosmic web stretching across billions of light years. Science progresses by correcting itself. That process continues today. Perhaps nowhere is this more evident than in discussions about life elsewhere in the universe. Although CERN is not primarily an astronomy laboratory, its discoveries influence our understanding of cosmic evolution. If particle physics changes, cosmology changes. If cosmology changes, our estimates of where life might exist also change. The observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Many stars possess planets. Current estimates suggest there may be trillions of planets capable of supporting liquid water. Given such staggering numbers, many scientists consider extraterrestrial life entirely plausible. Whether intelligent civilizations exist remains unknown. No confirmed evidence currently demonstrates contact with extraterrestrial intelligence. Nevertheless, the possibility continues, inspiring both scientific investigation and public imagination. Some conspiracy theories attempt to connect CERN with alien technology. Claims circulate that the Large Hadron Collider was reverse-engineered from extraterrestrial devices. Others suggest hidden collaborations with advanced civilizations. No credible evidence supports these ideas. The engineering achievements behind CERN are thoroughly documented. They reflect decades of human innovation, international cooperation, and incremental technological progress. Remarkable though they are, they require no extraterrestrial explanation. Still, one cannot help admiring what humanity has accomplished. An underground ring 27 kilometers in circumference. Magnets colder than deep space. Particles traveling at nearly the speed of light. Detectors capable of recording events lasting less than a trillionth of a second. Thousands of scientists from dozens of nations working together toward a common goal. Regardless of one's views on conspiracy theories, the reality is already extraordinary. Perhaps that is the greatest irony surrounding CERN. The genuine science is so astonishing that it often sounds fictional. Energy becoming matter. Invisible fields filling all of space. Particles appearing and disappearing. Quantum fluctuations within empty vacuum. Time slowing near light speed. Black holes predicted by mathematics and later observed in distant galaxies. None of these ideas require exaggeration. Reality has proven imaginative enough. Yet even after decades of research, the deepest mysteries remain unsolved. What is dark matter? What is dark energy? Why does anything exist at all? Are the laws of physics inevitable? Or could they have been different? Might our observable universe represent only one tiny region within something unimaginably larger? These are questions no one can yet answer. And perhaps that is precisely what makes science so compelling. Every discovery opens another door. Every answer reveals deeper mysteries waiting beyond. The story of CERN is therefore far from complete. In many ways, it may only be beginning. The final chapter explores what the future may hold for CERN, for physics, and for humanity's endless search to understand the universe. Part 9. Imagine standing on the shore of a vast ocean at sunrise. The horizon stretches endlessly in every direction. You can see only a tiny fraction of what lies beyond. Hidden beneath the surface are currents, mountains, valleys, and entire ecosystems invisible from where you stand. Modern physics finds itself in a similar position. Humanity has learned an extraordinary amount about the universe. We have measured the age of the cosmos to be approximately 13.8 billion years. We have mapped the cosmic microwave background, the faint afterglow left behind by the Big Bang. We have discovered thousands of planets orbiting distant stars. We have detected gravitational waves produced by colliding black holes billions of light years away. We have photographed the shadow of a black hole. We have identified dozens of fundamental particles and described many of the forces governing nature. And yet, the deeper we explore, the more we realize how much remains unknown. The Large Hadron Collider was never intended to provide every answer. It was built to ask better questions. Every experiment narrows the possibilities. Every measurement refines our understanding. Sometimes, discovering what is not true is just as important as discovering what is. For example, before the Higgs boson was confirmed in 2012, physicists had several competing ideas about how particles acquired mass. The Higgs mechanism was only one possibility. Once experiments confirmed the Higgs boson, many alternative theories had to be abandoned or revised. This is how science advances. Not through certainty, but through continual testing. One of the most exciting aspects of CERN's future involves the enormous amount of data that has yet to be analyzed. Every collision recorded by the detectors adds another piece to an unimaginably complex puzzle. Artificial intelligence and machine learning now play an increasingly important role in this effort. The Large Hadron Collider generates far more information than any team of humans could examine manually. Advanced computer systems help identify unusual collision patterns. These systems do not discover new particles by themselves. Rather, they assist scientists by highlighting events that deserve closer investigation. As artificial intelligence continues improving, researchers hope it will reveal subtle patterns previously overlooked. Sometimes the smallest anomaly leads to the greatest discovery. History has shown that nature often whispers before it shouts. Physicists are also preparing for the next generation of experiments. One major project already underway is the high-luminosity Large Hadron Collider. Rather than dramatically increasing collision energy, this upgrade will dramatically increase the number of collisions. Imagine taking a single photograph in dim light. Now imagine taking 1,000 photographs of the same scene. Details that were once hidden begin to emerge. The high-luminosity upgrade follows a similar principle. By observing vastly more particle interactions, scientists improve the chances of detecting extremely rare events. Rare particle decays. Tiny asymmetries. Unexpected behaviors. These may reveal entirely new physics. Beyond that lies an even more ambitious dream. Several international groups have proposed building a machine significantly larger than the current Large Hadron Collider. One concept is known as the Future Circular Collider. Instead of a 27-kilometer underground ring, this machine would stretch nearly 100 kilometers. Its collision energies would exceed those currently possible. Construction would require decades of planning and international cooperation. Whether such a project ultimately proceeds remains uncertain. The cost would be enormous. The engineering challenges would be unprecedented. Yet history reminds us that ambitious scientific projects often reshape civilization in unexpected ways. When people built the first powerful telescopes, they hoped to study the heavens. Instead, they transformed humanity's understanding of the universe. When radio technology was first developed, few imagined modern wireless communication. When researchers investigated quantum mechanics during the early 20th century, they could not foresee smartphones, lasers, magnetic resonance imaging, or modern computers. Fundamental research often produces practical technologies no one anticipated. CERN itself has already contributed innovations reaching far beyond particle physics. One of the best-known examples is the World Wide Web. In 1989, British computer scientist Tim Berners-Lee, working at CERN, proposed a new system that would allow researchers to share documents electronically across different computer networks. His invention eventually became the foundation of the modern web. Today, billions of people use technologies that trace their origins back to that idea. Medical imaging has also benefited from particle physics research. Advanced detectors developed for CERN experiments have influenced improvements in PET scanners and other diagnostic technologies. Superconducting magnet research has contributed to medical equipment, including MRI systems. Large-scale computing techniques developed for analyzing collider data have found applications in numerous scientific disciplines. In other words, even if CERN never discovers a new fundamental particle again, its technological contributions have already changed the world. Still, physicists remain optimistic. History suggests nature has many more surprises waiting. Some researchers hope to uncover evidence of dark matter. Others search for new symmetries. Some investigate whether the Higgs boson behaves exactly as predicted or hides subtle deviations from current theory. Even the smallest discrepancy could point toward an entirely new chapter in physics. Meanwhile, public fascination with CERN continues growing. Documentaries, podcasts, books, YouTube channels, online forums. Some focus upon genuine science. Others explore speculative ideas. The internet has transformed scientific laboratories into global cultural icons. Few institutions demonstrate this more clearly than CERN. For many people, CERN represents curiosity itself. Humanity's determination to understand the universe. For others, it symbolizes unanswered questions. The unknown. The possibility that reality may be stranger than anyone suspects. Perhaps both perspectives contain an element of truth. Science has always thrived at the boundary between knowledge and mystery. Without mystery, there would be nothing left to investigate. Without evidence, mystery becomes mythology. The challenge is maintaining the balance. Healthy skepticism encourages careful thinking. Healthy curiosity encourages exploration. Both are essential. As the Large Hadron Collider continues operating, new data will accumulate year after year. Most experiments will confirm existing theories. A few may produce surprises. One unexpected observation could force physicists to rethink decades of assumptions. That possibility keeps researchers motivated. No one knows where the next great discovery will come from. Perhaps a previously unseen particle. Perhaps evidence for dark matter. Perhaps an entirely unexpected phenomenon no current theory predicts. History repeatedly reminds us that nature is under no obligation to match human expectations. The universe has surprised us before. It almost certainly will again. And that is precisely why laboratories like CERN continue to matter. Not because they promise certainty, but because they embrace uncertainty. Because they seek answers through observation rather than assumption. Because every experiment, successful or unsuccessful, moves humanity a little closer to understanding the remarkable universe we inhabit. There is, however, one final question that transcends every scientific instrument ever built. Why do we continue searching at all? Why does humanity devote such extraordinary effort to understanding the cosmos? The answer lies not only in physics, but in something much deeper. Our endless desire to know. That question brings us to the final chapter. Part 10. From the moment our earliest ancestors first looked up at the stars, humanity has lived with questions. Who are we? Where did we come from? How did the universe begin? What lies beyond the horizon? These questions existed long before telescopes. Long before mathematics. Long before laboratories or particle accelerators. They are part of what makes us human. Every civilization has attempted to answer them. Ancient cultures explained the heavens through mythology. Greek philosophers searched for natural laws. Medieval scholars preserved and expanded scientific knowledge. The Renaissance ignited a revolution of observation and experimentation. Each generation inherited questions from those who came before. Each generation passed new questions to those who followed. CERN represents the latest chapter in that ancient story. Although its underground tunnels are filled with superconducting magnets, advanced computers, and detectors weighing thousands of tons, its purpose is remarkably similar to that of the first astronomers who carefully watched the night sky. To understand reality. To discover how nature works. To replace assumption with evidence. It is easy to become distracted by sensational headlines. Portals. Alternate timelines. Secret experiments. Reality shifts. Conspiracy theories often spread more quickly than careful scientific explanations because they appeal to something deeply rooted in human psychology. People enjoy mysteries. We are naturally drawn toward stories that suggest hidden knowledge. We like believing that extraordinary secrets exist just beyond ordinary perception. Throughout history, this tendency has appeared again and again. Ancient alchemists searched for the philosopher's stone. Explorers sought mythical cities of gold. Legends spoke of hidden kingdoms beneath mountains. Modern myths often replace magic with advanced technology. The stories change. The fascination remains. CERN has become part of that tradition. Its machines are so sophisticated that they appear almost magical. Its research investigates phenomena invisible to human senses. Its discoveries challenge everyday intuition. It is hardly surprising that such a place inspires imagination. Yet there is another perspective worth considering. Reality itself has repeatedly proven stranger than fiction. Just over a century ago, few people would have believed that invisible radio waves could carry voices around the world. That tiny electronic devices could perform billions of calculations each second. That surgeons could see inside the human body without making an incision. That humans could walk on the moon. Or that gravitational waves produced by colliding black holes billions of light years away could be measured here on Earth. Each of these achievements would once have sounded impossible. Science did not make them less astonishing. Science made them understandable. Perhaps that is its greatest strength. It does not remove wonder. It deepens it. The more physicists discover, the more extraordinary the universe appears. Quantum mechanics reveals particles behaving like waves. Relativity demonstrates that space and time are interconnected. Cosmology suggests that most of the universe consists of substances we still do not understand. Every answer expands the horizon of mystery. CERN exists because humanity refuses to stop asking questions. Will every mystery be solved? Almost certainly not. Some questions may remain beyond our technological reach for generations. Others may prove fundamentally unanswerable. History teaches humility. Again and again, scientists have believed they were close to completing our understanding of nature. Again and again, unexpected discoveries opened entirely new fields of research. Near the end of the 19th century, some physicists believed nearly everything important had already been discovered. Then came relativity, quantum mechanics, nuclear physics, particle physics, cosmology. Entire revolutions unfolded within a few decades. Today's researchers remain careful not to repeat that mistake. No matter how successful current theories become, nature always retains the right to surprise us. This humility distinguishes science from certainty. Scientists do not claim absolute truth. They construct models that explain observations. When better evidence appears, those models improve. This willingness to revise ideas is not weakness. It is one of science's greatest strengths. The story of CERN illustrates this beautifully. The Large Hadron Collider confirmed the Higgs Boson, completing a major prediction of the Standard Model. Yet instead of ending particle physics, the discovery highlighted everything still missing. Dark matter remains unknown. Dark energy remains mysterious. Gravity still resists unification with quantum mechanics. The origin of matter itself is not fully understood. In many ways, the greatest discoveries may still lie ahead. As technology advances, future generations may build machines more powerful than anything imaginable today. New detectors, new telescopes, new quantum technologies. Perhaps one day they will discover particles that explain dark matter. Perhaps they will uncover evidence pointing beyond the Standard Model. Perhaps entirely unexpected phenomena await. History suggests the universe rarely reveals its secrets all at once. It offers clues, fragments, hints. Each generation assembles another piece of the puzzle. The complete picture always seems just beyond reach. This continuing search reflects something profound about humanity. Curiosity is one of our defining characteristics. It drives exploration, innovation, discovery. Whether sailing across unknown oceans or investigating the smallest particles in existence, the motivation remains remarkably similar. To understand. That desire has led humanity from stone tools to space telescopes, from campfires to particle accelerators, from myths explaining lightning to equations describing black holes. Each step expands our perspective. Each discovery reminds us that the universe is larger, older, and more intricate than previously imagined. For those who enjoy mystery, CERN will likely remain fascinating. New theories will continue appearing online. New videos will analyze photographs frame by frame. Fresh speculation will accompany every major announcement. Some ideas may eventually prove insightful. Others will quietly disappear. That process is unlikely to end. Nor should curiosity itself ever end. Curiosity is valuable. It encourages learning. It inspires questions. The important distinction lies in how those questions are pursued. Science asks extraordinary questions, but insists upon extraordinary evidence. Conspiracy theories often begin with questions, yet sometimes accept conclusions before evidence exists. Recognizing that difference allows curiosity and critical thinking to work together rather than against one another. Perhaps the greatest mystery surrounding CERN is not whether it hides secret portals or alternate realities. Perhaps the real mystery is the universe itself. A cosmos nearly 14 billion years old, containing hundreds of billions of galaxies, each filled with hundreds of billions of stars. A universe in which atoms forged inside ancient stars eventually became planets, oceans, living organisms, and minds capable of wondering how it all began. That journey, from the birth of the cosmos to human curiosity, is extraordinary enough without embellishment. Whether future discoveries reveal new particles, hidden dimensions, or entirely unexpected laws of nature, one truth seems certain. The search will continue. Somewhere beneath the countryside near Geneva, protons will keep racing around a 27-kilometer ring at nearly the speed of light. Detectors will record collisions lasting less than a trillionth of a second. Scientists from every corner of the globe will continue examining the data. Most experiments will quietly confirm what is already known. Occasionally, one result may challenge everything. Those rare moments have changed history before. They will almost certainly do so again. Until then, CERN remains what it has always been. Not a factory for creating mysteries, but a place where humanity seeks to understand them. And perhaps that is the greatest mystery of all. No matter how much we learn, the universe always seems to have another question waiting.